Yes. Hello. I'm a little bit sick. I came all the way here just for you guys, so I appreciate it. Recap. So last week we gave like initial basic ideas of what is particle physics. We spoke about methods, how to produce particles, how to make particles. Then we started the introductory part. Actually there are three introductory parts. So the first was natural units. That's important because we're going to use that all the time. Right? H bar 1. And that means that we only have one unit, which is the unit of energy. And we'll be using GeV, simply because it's handy. So units of length equal to units of time. GeV minus 1. And units of mass is equal to units of energy, is equal to units of momentum. Is equal to GeV. And we started to speak about special relativity. And it's not a course in relativity, this is just to give you the necessary background. Basically a language, because we're going to use that all the time during this course, so that you get familiar, understand that most of this language many of you are already familiar with, so that's why I'm going over very quickly, so to spend the time on things that you're not familiar with. But I did give you the basics. We say the basics is the experimental basis, of course, is the Michelson-Morley experiment, based on which we say that there is two different observers that are inertial, namely they can be moving with constant velocity with respect to each other. When they are observing, both of them, a third event, right, they will disagree on the spatial location of the event, x, y, and z. They will disagree on the time of this event, but they will agree on the quantity which we call the interval, which is between two events, to be precise, an interval between two events, interval squared, delta s squared, is c delta t squared minus delta x squared minus delta y squared minus delta z squared. And then we started to use a new language, which may be not so new for you, I hope, which is a language of 4 vectors. So we said that each event is specified by 4 coordinates, which we call it x mu, which is x0, x1, x2, and x3, which is ct, x, y, and z. Then we introduced the matrix, which is known as the metric, eta mu nu, and I may occasionally simply write this g mu nu, these two lower indices, which is 1, 0, 0, 0, 0, 0, 0, minus 1, minus 1, minus 1. Also, I may call it g mu nu, these lower indices. And the conservation of the interval, delta s squared, I can write as eta mu nu, delta x mu, delta x mu. With the understanding of Einstein's summation convention, namely that when we're seeing an index that appears twice on the same side of an equation, once as an upper index and one as a lower index, we're really summing over this index, and it's called a dummy index. So here there are 2 dummy indices, mu and mu, which go from 0, 1, 2, 3. So we have a sum of actually 16 terms, but as you can clearly see from this simple matrix, 12 of these terms are 0. So we have only 4 non-zero terms here. Then we define the Lorentz transformation as a transformation that takes us from one coordinate system, one inertial coordinate system, to another inertial coordinate system. And it's not just any transformation, it does something special, which is conserving the interval. Lorentz transformation is a transformation between two inertial coordinate systems for example x mu and x mu prime that conserves the interval. So we write it as an element of a matrix. We write this lambda mu prime rho, and the conservation of the interval denoted by, and conservation of the interval implies that it fulfills the equation eta rho sigma is equal to lambda mu prime rho lambda mu prime sigma eta mu prime. And as you have noticed, I do use, it's a diagonal here. It's not one on top of the other, but there is a diagonal here. I won't get into that right now, because there is no need. Okay, but it's always written in diagonal. Yes?
Can you write a little bit bigger?
Can I, what?
Write a little bit bigger.
Yeah, I can try.
Oh, thank you.
Okay, and I gave you a few examples of Lorentz transformations. One is a simple rotation. Large rotation in the when time is one of the axes, or rotation, or let's say the x and time. That's called the boost. That's what you're familiar with from supposed to be familiar with from first year. Understand though that often we generalize the first year, so you have seen that. So it's the same. We are consistent with each other. So for example, lambda mu prime nu. Example. Boost can be written as minus gamma, sorry, plus gamma minus gamma beta minus gamma beta gamma 0 0 0 0 0 0 0 0 1 0 0 1. Where beta is b over c and gamma is minus beta squared. Then we spoke about the scalar product, and said A dot B. Scalar product A dot B is defined as A mu B mu, where B mu I can use the metric to lower indices. And mu, B and mu. The importance here is that 4 vector with lower indices live in a different space than the 4 vector with upper indices. They don't live in the same space. These are vectors and dual vectors. Okay, and this is invariant under Lorentz transformation. So this is also equal to A mu B mu eta of course A mu is A dot A is A mu, which does not have to be positive. It's a square of the norm. It doesn't have to be positive in the world in the special relativity. The last thing we spoke was about time dilation. So the physics is that time dilation. If you have two observers, one of them is holding a clock, like me, and the other observer sees, so in my reference frame, this clock is not moving because it's attached to me. Right? My perspective, I'm fixed, you are moving. Or this clock is moving. From your perspective, I am moving and you are steady. Right? From my perspective, this clock ticks, let's say every second, or any interval that the manufacturer of this clock decided. That's called the proper time. But from your perspective, there will be two ticks of the clock, which will be the lower delta tau, or delta ET, is equal to delta tau, proper time, as measured by an observer holding the clock. And delta t prime is gamma dt. This is the time as measured by an observer that sees the clock moving. As I said, we see that all the time. If we look at cosmic rays, we're seeing various particles, and we know that their lifetime is very short, so they should not be seen. But since they're moving very fast, then they actually do reach the detectors on Earth, especially muons, because they are very abundant. Right, so before the idea today is to finish with that, so we can move on to start speaking about the standard model. Questions about anything we said so far? I said maybe.
How can you measure time with no philosophy? But when you talk about time, from my perspective, you can measure it without feeling what time is. So how basically time can be measured from אפשר אולי לדבר בעברית,
not everybody will understand it, we can ask if you can copy.
בסוף זמן כשאני מודד אותו, אז ואני רגע רוצה להשוות אותו בין שתי מערכות שונות, אז איך הוא רגע מהיסוד שלו, איך התחילו למדוד אותו? כי זמן זה משהו שקשה להגדיר אותו, בלי שהוא בפני עצמו, אבל שהוא לא יהיה תלוי בו.
What this says, in Newtonian mechanics, you're used to the idea that different observers look at space from different locations. As I gave an example, let's say that we're sitting in a stadium. You're on one side of the stadium and I'm on the other side of the stadium. We're watching a soccer match, and somebody scores a goal. And you'll say, yes, this is to my left. And I said, no, this is to my right. And we'll both be fine. And you're fine with that. You don't have any problem with that, right? We both saw the same thing. You saw, okay, I saw that there is a goal, but I think this is to my left. And I said, no, this is to my right. This is simply depending on where we are, right? So the same thing here, right? Time is relative to the observer. Same way as space is relative to the observer, time is relative to the observer, right? We are both seeing the same things. We just attribute different times to it. Okay? Now, it is one way to think of it. Now, you have to, if you think a little bit, you imagine, you realize that every way to measure time will give you exactly the same thing. So it doesn't matter if you're talking about mechanical clock, electronic clock, atomic clock, biological clock, you'll get the same thing. And I'll give you the classical example, which is easy to visualize. let's say that you are sitting now in a spaceship, and you want to measure time. So you're building a time device. What is your time device? The time device, the simplest that you can think of, this is your spaceship, and you're sitting now in a spaceship. Right, you're the astronaut here. And you want to measure a time device. So the time device will be the following. You're putting here a source of light, and you're putting here a mirror. Okay? And your time device says that at a certain point, you're releasing a photon. The photon goes to the mirror and back. Since your time device knows exactly the time that the photon was released, it knows exactly the time the photon was detected, then you know delta t between emission of the photon and detection. Detection can be your eye, doesn't matter. The time between the emission of the photon can be some chemical reaction that emits a photon, right? And the time that the photon was observed, detected.
אז זה מתקשר רגע לנושאים מלכתחילה של מה זה זמן אצלי, כאילו איך אני יכול להגיד שאולי שנייה אצלי היא יותר זמן, שוב, אולי אני מתפלסף יותר מדי, אבל זה יותר זמן מאשר שנייה במערכת אחרת, כי בסוף, איך שאני רואה את זה, הזמן הוא תלוי באיך שם, איך שאתה תופס את המרחב.
No, again. Imagine a way of measuring time. How would you measure time? How do you measure time? Let's say there is a cuckoo clock, right? So it's based on the idea that there is one thing that goes in one direction, then it goes back to the other, and then you know how long it took. So okay, a day. What is a day? Earth is rotating, spiraling. Everything, every mechanism that you can think of would work essentially the same way. There is a point where something happens, and then after a while, some other thing happens. Then you can measure the difference in time between these two events. It's always easier to think in terms of events. So the simplest I can think of is the first event is emission of photon, the second event is absorption of photon. And when you think of it, biologically, that's what happens in your cells, for example, right? There is some chemical reaction inside your cell. I don't know, some energy is released, emitted, whatever, right? You're living, you're talking, whatever, right? This is what happens in atomic clock, right? There is some rotation of an atom, which can be emitting a photon. Or there is absorption of photon, which causes the electron to go up. This is what happens in an electronic device, right? There is some spike, electronic spike. Everything always works like that. So this is a prototype of every clock that you can think of. Okay? And this will work. You'd say, okay, I mean, I've emitted a photon. The photon, this is the first event, the photon came back. Second event, I can, there is a time difference between these two things. I mean, in the philosophical way, you can say, okay, time represents a change, right? If there is no change, nothing happened, then you cannot say anything about time. Okay? The important point here is that the time is relative to the observer. And that's very easy to see, because if now you are an observer that is sitting outside and watching this spaceship, right now you're here on Earth, watching the spaceship, right? The spaceship moves, right? So the spaceship, from your perspective, starts here, and then it moves, and continues to move. So this photon, right? Device here and the wheel here. So the time that the photon was emitted, let's say the spaceship was here. By the time it reaches the mirror, from your perspective, the spaceship is already here. So the actual distance that the photon travels is that. And then it travels back here. The photon travels at the same speed, the speed of light. It's a different distance, it's a longer distance, then the time difference will be longer. This is just to say that two different observers right? A and B. The astronaut and somebody who's staying here and watching him here measures different times. But the idea of how to measure time, yeah, this is associated with something that changed. Something happened. Nothing happened, and yeah, philosophically you cannot measure time. Everything is fixed, studied, there's no time. Yeah.
צופים הסכימו, שמתם טוב, הסכימו לא רק לאינטרוול, הסכימו גם על סדר האירועים, נכון, אם קבוצה שלי פי הגול, קבוצה היריבה פי הגול, לא משנה באיזה מהירות אני נע, זה תמיד יתפסות פסס.
נכון. Time can be stretched, but you cannot reverse time. You cannot go backward. You can stretch the time, but you cannot reverse the time. Oh, you can see, actually, yeah, you can see an event. Maybe you can see if you're moving fast enough. Maybe you can see something happens before you. I have to think a little bit about it.
It depends if those stays like was there, right?
Okay. Stopping here. Okay. Any further questions?
Do you have notes also about the next lectures or only for the...
I do have. Wait, one step at a time. Sit here, understand, and we'll be fine. Okay, now the next thing I want to do, I want to finish that part of special relativity, because really this is not a course in relativity, but this is just to give you the basic background that you need. And it's fun. Some of you claim that you've seen that, but you forgot, so I'm just refreshing your memory. Okay, so a few more things about special relativity, which again will go as fast as reasonable. Just write only these two pens. So for velocity, acceleration, for force. Yeah. So if you want to describe a motion of particle, in classical mechanics, normally we would say the coordinate as a function of time, right? X as a function of t, y as a function of t, and we'll see how the forces are acting between them. In special relativity, this doesn't make much use, because it's not very useful, because time is itself a coordinate. So we need to find a better way. The better way is to specify what's called a world line. Just draw a 2D, and we put all the space in one direction. This will be x. And this will be CT. And the word line is just a line that represents the motion of the particle in space. Let's go somewhere else. So this curve is called the word line. Okay. This was the word line. And the description of the motion, right? We just need to specify some parameter along the motion. You can call it lambda. Then we can say x nu as a function of lambda. So lambda can be a simple number, right? So lambda can be lambda equal to 1, 2, 3, 4, 5, 6. So in every point lambda, we know all the 4 coordinates as a function of lambda. Now we can choose as a lambda anything, but what will make the most sense?
Proper time?
The proper time, right? So instead of lambda, we just use tau. We write down x mu is x mu of tau.
But for photons it will not work.
Yeah, for photons it's not going to work, but we're less scared about photons at the moment. Now we can define the forward velocity. What is the forward velocity? If x mu is a function of tau, what will be a forward velocity? Dx mu
to the d tau.
to d tau, right? So this is definition. U mu, that's another 4 vector, is defined as dx mu over d tau. Any questions to me? So again, x mu, u mu is defined at every point along the world line. Every point, there is x mu, which is a function of tau, and then also u mu, which is a function of tau. Right? Now remember that delta tau squared is 1 over c squared eta mu nu, delta x mu, delta x nu. So we can write down d tau as square root of dt squared minus dx squared over c squared, which is dt square root of 1 minus dx over dt squared over c squared, which is dt square root of 1 minus beta squared. So u0 is d ct over square root of 1 minus beta squared dt. So this is just c over square root of 1 minus beta squared, which is just gamma times c. And ui, the spatial part of the forward velocity, is just dxi divided by square root of 1 minus beta squared dt. So 1 over square root of 1 minus beta squared times dxi over dt. This is just gamma times vi, or vi, consistent, or gamma times beta I. What is the norm of the forward velocity? It's a 4 vector, so it has a norm. Uni? Well, yes, okay. I'm using u squared. U squared is u mu. So eta mu nu mu. So eta mu nu dx mu over d tau, dx nu over d tau, which very bluntly and completely and mathematical, I would simply write as eta mu nu dx nu over d tau squared, which is just c squared.
Can you explain the last?
Yeah, it's mathematically incorrect. So I cannot really explain. Okay, next. For acceleration, what's the definition for acceleration? Sorry? With respect to? Tau, of course, right? It's very simple. A mu is defined as du mu over d tau. What will be the force? What? MAU, right? So F mu is M times A mu. Very simple. M du mu over d tau. Once you get it, the things are pretty straightforward. There's nothing much you can do. Which is, of course, the relativistic version of Newton's second law. Right. Now, out of curiosity, as discussion, for acceleration is perpendicular to the for velocity. Right. For acceleration is perpendicular to the for velocity.
Because it has constant net length.
What?
Because it's constant length.
No. A mu. U mu. Right? Is eta mu nu du mu over d tau. U nu. That's fine. Which, because of symmetry, I can write as 1/2 d eta mu nu u mu u nu over d tau. This is mathematically correct. But what is eta mu nu u mu nu nu?
It's u squared.
C squared, right? So it's constant. So this is 1/2 d c squared over the tau, which is 0, because this is constant. How can it be?
What's the problem?
How can it be that the for acceleration is perpendicular to the for velocity always?
As you get fast in the 3D space, you get slower in the t space. The time
Sort of, yes. Sort of, yes. I mean,
There is a dependency in
exactly.
the,
There are four, yeah, right.
in the term.
Yeah, exactly. I mean, there are four components, but only 3 independent. Once you set up the 3 independent components, the fourth component is already set, so that gives you this constraint.
Can you explain again why?
Well, first, this is mathematically simple, right? So how can it be? It means the acceleration does not really have 4 independent components. Once, because acceleration is derived from the velocity, so it only has 3 independent components, and once these are set, the fourth one is determined by that. So don't get too nervous by that result. And of course, the next obvious result is to look at the momentum. So for momentum, energy and momentum. How will I define the full momentum? Right, it's very simple. For momentum is P mu, it's just m dx mu over d tau, or m u mu. Can you read that, or that's too weak? I don't know. What was the pens here? None of them was really working. So, what is, I just erased that, but what is p squared? The norm of the momentum?
M squared, c squared.
Right, m squared, c squared. What is p0?
MC gamma.
Gamma and c. What we had, and what is pi? The spatial part?
Gamma beta MC.
Gamma beta I mc, or gamma m pi. Is this clear to everybody? These are getting important, by the way, because we're going to use them quite a lot. So, in the limit of small velocities, right, v much smaller than c, that's back to the Newtonian limit, right, which means that beta I is much smaller than 1. What do we get from gamma?
it's 1.
What?
Yeah, it's 1.
1 plus beta squared divided by 2.
Yeah. Right. Then the next term in Taylor expansion, gamma is 1 plus beta squared divided by 2. Right, that's a Taylor expansion of that, right? Is there anybody who did not see Taylor expansion? There is a reason why I ask. I did encounter people here, even in third year, that did not see Taylor expansion. So don't be shy if you did not see.
You taught us in mechanics 2 years ago.
I know what I'm teaching. I don't know what other people are teaching, and I don't know what courses you took. In the limit V much more than C, gamma is greater than 1. Sorry, not greater, is equal to 1 plus beta squared over 2. So what do we get for P0 if we just plug that gamma? What is P0?
MC plus MC times beta squared.
MC plus MC plus beta squared over 2, so we can write this M 1/2 M V squared over C. What is Pi?
MV plus
MVI
half
MV plus O of V cubed. V cubed over C squared. That's very small.
How we got the second
What?
with the alpha and the MV value? MV squared.
Half beta squared times MC. Right? Half beta squared MC, beta is V squared over C squared. Yeah? Everybody's happy? So, what is that?
Oh, it's MVI.
Right, so how do you call that?
Newtonian.
That's a Newtonian momentum. Right? What do we do with that, Sport? Is the first equation.
Energy?
What do you do with it?
It's the energy divided by C.
Right, so we multiply it by C. So if we multiply by C, then we get C times P0 is MC squared plus 1/2 M V squared. Last corrections. Correction will be plus O of beta to the 4. Alright. So, what is that term? That's kinetic energy. What is that term?
Rest energy.
Energy.
It's a magic rest. Right?
Magic
That's a
energy.
magical term. It was not there. That's the first time that an energy term appears right out of the equation. Einstein just wrote this equation. Look how simple it is once you accept this idea. And voila, you got a new term. It has units of energy, and what is the rest mass energy? Are you familiar with one of the debates of the late 19th century about how old is the solar system? How old is the sun? You know that? Oh, it's a beautiful story. So one of the greatest physicists of that time was Lord Kelvin, and versus somebody who didn't study any physics at all, but was maybe the best scientist of all times. Who's that?
Einstein.
Darwin. What was the claim? The question was how old is the Earth and how old is the solar system? How old is the sun? So Kelvin, in new physics, right? He could calculate the rate of energy emitted from the sun. So he could calculate how much energy there is inside the sun. And he could estimate how long the sun was. The sun must have been active. And the idea was that life on Earth could not have been existed longer than that, right? Which makes sense, right?
You were completely wrong by.
He was completely wrong, but anyway. He was the best. He was one of the top physicists of that time. And Darwin didn't study any physics, but of course he knew biology, invented most of it. And he had some geological friends, so he could estimate how long it takes the glaciers to form the valleys. And then I think so. We can check it out. And the numbers they found were many orders of magnitude more than what Kelvin said. Kelvin, I think, said something in the order of tens of thousands of years, maybe millions. No,
You said something like 40.
and Darwin said it must be many orders. It must be much longer than that. Right? And what was of course, it was correct. Many things. What was the origin of mistake? This term, right? That is where the energy of the sun comes from.
Know how
Right?
the sun works.
What?
And you didn't know how the sun works.
Yeah.
At all.
Yeah, he did not know about that. Well, he did not. He knew about kinetic. He knew about all the energy that was there, but he didn't know about that this is a source of energy. He didn't know about nuclear reactions, obviously. He had no way of knowing that, which is really the source of energy from the sun. So the sun is way older than what Kelvin could calculate. About 4 billion years, 4 milliard, and the Earth was from around that time. So. Okay. It's a nice anecdote. So overall, if we take these two together, write down P0 so it is E over C is just pi squared plus m squared c squared. All that to the power 1/2. I just plug it here. In here. This one. All right. Example. So, April 25th, 2022. That's the best of my knowledge. That's a new record of colliding two particle beams in CERN. Energy of each beam was 6.8 TeV. It's on April 22. Beams. Beams of protons. Beams of protons. Collided in CERN. What's the Lorentz factor? What's the Lorentz factor?
Naturally.
Lorentz factor does not have any units.
1.
What's the Lorentz factor? What is the Lorentz factor of the beam?
Take the energy,
300.
קח את האנרגיה, תחלק ל-M0C בריבוע, וזה...
קדימה. שלוף עכשיו.
Yes.
What's the energy? What's the Lorentz factor? What's the Lorentz factor? This is the energy, right? 6.8 TeV.
המסה של פרוטון?
What's the proton mass? Do you remember? MP?
One mass.
G.
One word, one game.
GeV, yeah.
7.2.
What? Lorentz factor?
כל היחס בין טרה ל-G.
שזה?
ששת אלפים שמונה.
אה?
גם PL?
קצת יותר. So gamma is E divided by MPC squared, right? Which is it's divided by 0.938, which is that's the Lorentz factor. And what's the velocity, guys?
0.99999.
How many nines? What?
A lot.
How many?
Enough.
How many?
Use the logarithm.
8.
8, right? 8 nines, right? So beta. That's right. Very good. So how far is it from the speed of light?
Very good.
Very close. How much below the speed of light is that?
0 point something something.
No, meters per second. Yeah.
In which frame?
10.
So much what?
10.
No, why 10?
Not 10.
What is the speed of light?
3 times 10.
1.
3 times 3 times 10 to the 8 meter per second. We have 8 nines. How much?
3 meters per
3
second.
meters, right? So this is just 3 meters per second. 3 meters per second short of C. About 11 kilometers per hour.
On the frame of
I
reference.
think some of you
Earth,
can run even faster than that. What?
On the reference frame of Earth.
Yeah, in the experiment. They're doing the experiment. You understand the experiment, right? They're taking particles, they're accelerating them, and they let them collide. They try to accelerate them as fast as they can. This is the fastest, to the best of my knowledge, this is the fastest that was ever reached in CERN, 6.8 eV. I told you, cosmic rays you can get much higher energies. But this is man-made. Right? This is man-made, protons at 6.8 eV, short of the speed of light by 6.8 meters per second. How long did it take to cross the ring of CERN? You know what's the side, the circumference of the ring in CERN? 27 kilometers. This is a ring. Right. Geneva is somewhere over here. It's been, a bit below the city, right? And that's 27 kilometers. How long did it take it to complete one loop?
That divided by C.
What?
10 to the minus 6.
10 to the minus
Slightly more.
7.
No.
Microseconds.
I don't know. I got 90 microseconds. Check out. So the time that I got was 90 microseconds. Check it out. This, by the way, some of the, I told you, this is not a too difficult course. I mean, this is the type of questions you should be able to answer without even thinking. Right? Few others, but start with that. I give you the homework today, if I'm not too serious. But the last thing I want to do, nearly the last thing, two last things I want to do about special relativity. What if we have a composite system? Why am I erasing that actually? What if we have a composite system of two particles? So let's say we have two particles and we let them collide. If we have two particles, right, they have four momenta, P1 mu and P2 mu. Right. Then m squared, right, is P1 mu plus P2 mu squared, which is E1 plus E2 squared minus E1 plus P2. These are three vectors, right? When you put a vector, so that's a three vector. So this is M1 squared plus M2 squared plus 2 E1 E2 minus 2 E1 E2. So the mass is not a simple sum of the two masses. Okay, take a second to digest that, and then digest it a little bit further in the work. So this quantity, P mu, which is E1 plus E2 squared minus P1 plus P2 squared, has a name. What's the name? What? No, it's called invariant mass. So, scalar.
Did you forget the norm of P1 and P2?
I don't think so. Gets into M1.
Okay.
And then, yeah.
Explain,
No, you do it at home. Come on. Just open it. It's
no, I didn't understand the first,
which one?
ההשוואה הראשונה, של האם בריבוע שווה ל...
פי אחד, ניו בריבוע. הנורם של פי אחד, זה בדיוק מה שרשום פה. היה רשום פה. פי מיו שווה ל-M בריבוע. C שווה 1, כן, פי מיו, מיו ופי מיו, זה M בריבוע, מיו שווה 1.
אוקיי, and why, למה שווה לחלק השני ל-1 ועוד עם 2?
זה פי מיו. Think of it a little bit at home, you realize that, okay?
So what is the difference between P1 vector and P1?
I have a system which contains two particles. They collide. P vector, that can be important. P vector, I'm only referring to the three momentum. Right, the regular moment, Newtonian momentum. P mu is a 4 vector. Mu equals 0, 1, 2, 3. This is the invariant quantity, invariant mass. When I say invariant, what does it mean?
זה לא משתנה כמובן.
It means that two different observers that have different frames would agree on that. That means invariant. So invariant under Lorentz transformation is correct there. Right? So we have two different observers. Again, as I said, they will disagree on various things. They will disagree on the energy of each particle. Right? Because in one frame, for example, I could be moving with the particle. So the energy is just the resonance energy. And if I see the particle moving, then it also has a kinetic energy. Right? So they'll disagree on the energy of each individual particle. They will disagree on the momentum of each individual particle. They will agree on the invariant mass. Yeah?
So in the first lecture you told us that with any equation we will see in this course, the mass is not determined. But in here you say two observers will agree on the mass.
Yes.
In
Because P mu P, the
special
norm of P,
relativity.
because the norm of P mu,
So
the norm of P mu is invariant.
if I know P mu, I know the invariant mass. So the mass is well defined. So why you told us it's
Alright, here I have a
variable.
situation. Here I have a situation where I have two particles.
Okay.
Right?
Mhm.
I have two particles. Where? Okay. Where does it go? Right. For example, if we have a situation where we have one particle that decays into two particles, right? Now we don't necessarily see the initial particle, the parent particle, but but we will see the decaying products, because these two particles, for example, can be much longer lived than the parent particle. Right? So if we make different experiments and we always see these two particles, we can compute their mass. We'll know that this must be the mass of the particle, unless there is a third particle involved somewhere in the decay. Right? Or alternatively, let's say that we're seeing different experiments, and we're seeing collection of particles having the same mass. That can tell us something about the origin of this of these particles. They may be coming from a certain particle. Does that answer your question?
In the first lecture, you told us that the mass is free variable, that's not determined by our equation that we will see.
Mass here is a constant.
Yeah.
No, okay. You're mixing two things. Free variable meaning that it's not part of the theory. The theory does not predicts what should be the mass of each particle. Okay. I think that's what that would be interesting.
But the momentum will be well defined, so the environment.
Once we know the mass, then we know what is the. Or once we know the momentum, we know what is the mass. Yes. But in the theory, we're going to start talking about the theory in 2 minutes, right? But the theory itself does not tell us what should be the masses of the particles. It can tell us about interactions, which interactions can occur, which interactions cannot occur, given that the mass is known.
But here you say, if I have the momentum, I have the mass, right?
Yes.
So we will not have the momentum?
The momentum is not an ingredient of the theory. This is it's a variable.
The momentum can be changed. You don't know the momentum at any time for any given particle.
Okay.
Right. The momentum is not. When I speak about the theory of the standard model, right, the theory, I thought it was clear. Maybe it was not so clear. When I speak about the theory of the standard model, right, it discusses what particles there are, what type of interactions occur between these particles, when they can occur and when they cannot occur. Okay? So I can tell you that one particle can decay into other particles, and I can tell you how to calculate the lifetime of a given particle. But there's nothing in the theory that tells us that the mass of the electron needs to be such and such, or that the mass of the muon needs to be such and such, although the muon and the electron are considered as elementary particles.
Okay.
Okay? That's what I meant. The theory itself does not tell you that. But once you know that this is the mass of the electron, or this is the mass of the muon, or this is the mass of the Higgs boson, right, that's part of the reason it took so long to find the Higgs boson, because nobody knew what is the mass of the Higgs boson. There was nothing that could give us any hint of what the mass of the Higgs boson should be. Well, there were some hints, but they're not determined.
Okay. Thanks.
Okay?
Yeah,
So that's what I meant. Here, this is a tool of making calculation. Now, what I mean is that this mass is invariant. It is not conserved, in the sense that you can have a massive particle that decays into other particles.
Yeah.
Right?
Okay.
So the mass is not conserved, but it is invariant. Invariant meaning two observers look at the same particle with two different reference frames. They will determine that the mass is the same. Okay. Right, again, the form momentum is a vector, right? So it changes from one frame to the other frame. But this is a scalar, so it does not change from one frame to the other. There's some miracle here that we can take a vector and make it, miracle, right? But the vector that is not invariant between two frames, you can take a scalar product with itself. The norm is invariant. Okay? It's not a miracle, it's just the way it is. It's fine? Yes? No? Maybe?
Why is it invariant?
Why it is invariant? Well, you can see it from here. Again, from the fact that it goes back to the definition of u mu, saying that u mu is c squared. And m is just some constant. M for me is just a number that multiplies that.
Is the
This is the rest mass. This is the rest mass. Right? Rest mass. Yeah.
אז במטרה להפעיל אחד בריבוע והפי שתיים בריבוע שלך.
כן? חלק מהם הלכו יחד עם ה-E. You'll see it from here, right? There's Pi. P vector is Pi. P0 is the E. Do it at home. Okay, the last thing I want to say before we begin is, again, just a covariant notation of derivatives. So since I will use it all the time, just to make sure that you're all with me. So we said it once. So it's called a covariant notation. Covariant notation of derivatives. So I will use d mu, which is d over dx mu. So d over dx mu is an upper index, and d mu has a lower index. This means dt and blah blah, which is, when I say dt, that's a shorten of d over dt. So that simply means dt, dx, dy, dz. Right? It's d over dx, d over dy, d over dz, d over dt. When I say d mu is an upper index, that is d over dx mu, of course now is a lower index than x mu. That is nearly the same. That is dt and minus blah blah. So this is dt minus dx minus dy minus dz. Yeah? Have you seen that before? Get used to it. That's the language we're going to use. Questions? That's actually a little bit even more than you need about the standard, the special relativity.
Can you go over just shortly about the invariant and observation of שינוי ההבדל בין invariant לשינוי אנרגיה לשינוי.
Yeah. Okay. Guys, one by one. Don't mind asking questions, but please ask them. I cannot even hear the question. So, when we say invariant quantity, right? Invariant quantity means that two different observers that have two different reference frames, both are inertial, but namely they are moving with respect to each other. They both agree on this quantity. That is the meaning of an invariant quantity. A conserved quantity is a quantity that is not changed in the process. Okay, so this is not the same. Yeah.
Is it relevant to ask about the second definition? I didn't understand why.
Which definition?
Of the, yes. I don't know, it's will with the minus sign. I didn't
Yeah.
understand why.
Well, that's related to this matrix eta, the metric. So how do we get to, how do we raise and lower indices using this matrix? So we have this extra minus sign that enters into the spatial part of the derivatives. To learn more, come to the course in GR. Right now, we'll just memorize that. That's what we're going to use. This will be the main way of making derivatives. So when I say that, that's what I mean. And when I use that, I mean this extra minus sign. And I often use d mu, which will be denoted. This is called D'Alembertian. It's a generalization of Laplacian. Okay. Just that you know.
So this
in the context of the wave.
Of waves, likely. I know, physics is the same physics.
The Laplacian square.
The Laplacian, not necessarily Laplacian. Like Laplacian is number square.
It's
called-
supposed to be square.
What?
The squared
No, no.
Yeah,
I think. It's not.
Okay.
Maybe I'm wrong. Check it out in the textbook. Okay. Further comments, questions, or concerns? No concerns at all. Okay. Now let's start. So what I'm going to do now is to give you some overview of the standard model. What is it made of? How it is, and then we'll go during the semester. We'll go one by one to the basic ingredients of the standard model. Do you need a tutorial about special relativity? Who thinks they do? Raise your hand. Who thinks they don't? Raise your hand. Most people don't really know. Okay. It's mainly to learn the language. Okay? It's not a course in special relativity. It's mainly to refresh your memory and make sure that we all speak in the same language. Because this language we're going to use all the time. Okay? That's the main purpose of that. Okay, if you have troubles, let me know, because I take it that you all said that you have learned it quite well with OFAC. So I tend to believe you, unless proven otherwise. Okay. So now we're going to start by introduction to the standard model. The name is quite impressive, right? Standard model. So it definitely is one of the greatest success of physics in the 20th century. It's been a numerous number of experiments and theories that falls into here very beautifully. But before we describe what they are, I would mention a few drawbacks. So we know today that the standard model is not the final word in particle physics. We know that there is some physics beyond the standard model. Why do we know that? So, for that I said, so we believe that the standard model is some effective low energy theory in a very analog way to the fact that Newtonian theory is an effective mechanics theory for relativity when all the velocities are much smaller than the speed of light. Right? So when v is much smaller than c, then we can use Newtonian physics. Then we're fine. But we know that when we go to higher speeds, it's not going to be fine. And the same way about the standard model, we know that at low enough energies, it's perfectly fine. But when you go to some energy scale, this becomes less fine. So, why the standard model is incomplete? That's even before I start. Why do I say it's incomplete? What is not? So the first thing is that it is not consistent with general relativity. It's consistent with special relativity. That's the way it was built. But it is not consistent with general relativity. So, SM cannot explain gravity. Another things that you learn. There are evidence that most of the universe is composed of matter and energy that we do not know about. There is this thing that is called dark matter. What is dark matter? Right? In the solar system, where is all the matter in the solar system? In the sun. And the sun emits light, so it can be seen from the other side of the galaxy. Right? And And we can say that about 99% of all the mass in the solar system is in the sun. So we could imagine that this will be true for any solar system, right? In the galaxy and in other galaxies as well. But much to the surprise, how can we measure the masses then? How can we measure the mass of a galaxy?
השקיפות של האור.
I don't know.
Luminosity.
Give you a reason. I give you a hint. This was done in the 1930s by an astronomer called Fritz Zwicky. That was nearly 90 years ago. So we didn't have, we could not detect gravitational lensing. Right. Rotation curves, right? So you can measure the velocities by Doppler shifts. So you can measure the velocities of clusters of stars or rotation curves. But the rotation curves of the galaxies themselves, they were done by Vera Rubin. I met this woman. She died a few years ago. That's why the new observatory is called Vera Rubin Observatory. She did the measurements in 1960. So one way is to look at the luminosity, right, all the stars in the galaxy, and see, basically measure the light. And there is some conversion table that tells you, okay, a bigger star would emit whiter light or whatever, right? And then you can measure. Another is to simply look at the Doppler shifts, which is affected by the gravitational potential of the galaxy, right? And then you say, okay, by the gravitational potential, I know what is the mass, or how it is distributed. So there is a difference. How big is the difference? I mean, you'd imagine there will be a difference, right? It's astronomy after all. There's you cannot measure precisely. What's the difference?
20.
A factor of 6. There's 6 times more mass. 6 times more mass that you can infer from rotation curves, from gravitational potential, so mass that interact with the gravitational potential, than the mass that you actually see, the light that you can measure from these from the stars in that galaxy. It's a factor of 6. It's not like 10% or 20% that you say, okay, fine, right? It's big. That's, by the way, why it was suggested that maybe it was by Milgrom from Weizmann Institute in the 1970s, says, okay, maybe Newtonian laws are not working on that scale. It's called modified Newtonian dynamics. It was never proven to be right, but it's interesting. So that's called the dark matter problem. So dark matter that contains of about 25% of all energy in the universe. So we know there is a matter, but we just can't see it. We don't know why. Right? And it's not part of the standard model. Anyone else?
Dark energy.
Yeah, what is dark energy? Not dark matter. It's not related. What is dark energy? Yes. So Einstein, right? The modern cosmology is based on Einstein's general relativity. And then you can find a solution which basically gives you the Big Bang, right? So there was a starting, initial conditions, and the universe expanded, and then since then it's, because of gravity, it pulls it back. So you'd expect it to pull back or slow down. But a new discovery from 1999 showed that the universe is not slowing down, but is accelerating. So that's why would we accelerate it? So there's this thing called vacuum energy. And now there is a vacuum energy in quantum field theory, but not at that level. And when you do the measurements of the expansion of the universe, you find out that most of the energy is in that dark energy. So the origin, dark matter is a matter that at least we can see its influence gravitationally. Dark energy is something which we have no idea what it is at all. That contains about 70% dark energy. About 70% of all the energy in the universe. So all the matter that we have here, and in the sun, and in the other stars, and Earth, and other planets, and everything that we have, is only about 5% of the universe. The rest we got no idea what it is. Right? So, and the standard model is about this 5%. Right? So all you have, this standard model is a 5%. 5% is normal matter. These are the electrons and the protons and the atoms and everything. Okay. another problem. So I said it's incomplete. The other thing is the masses of neutrinos. Particles called neutrinos, denoted by news. Neutrinos are nearly massless. So photons are consistent with zero mass. Neutrinos, they thought for many years to have a zero mass, but then it was discovered that they do have some mass. It's very, very small, but it's not zero. And the standard model does not really explain that. In the standard model, neutrinos are massless. Yes?
Their mass is small even as they detected because the effective mass is also small, or only the
masses, they're let's say, proper mass. Mass is some basic ingredient of a metal. Okay, so we thought that they were massless. Then we saw a phenomenon which is known as neutrino oscillations. I don't know if we'll have time to discuss that. Essentially, one neutrino can convert into another neutrino, and that can only occur if the neutrinos have mass. That's another problem. The third problem is what's called as the matter-antimatter asymmetry. Symmetry. It's a very interesting, let's say, philosophical question, right? Because we know that all the matter we have is made of regular particles, matter, right? We're all made of matter. But within the framework of the standard model, for every particle there is anti-particle, right? And there is nothing, it's completely symmetric between particles and antiparticles. To the best of our knowledge, all the universe is made out of regular matter. We've never detected any evidence for antimatter anywhere in the universe, which means that something had to break the symmetry, because all the equations, and you see that, are completely symmetric between matter and antimatter. What is that? Why is that? What happened? How it happened? And it's not within the realm of the standard model to explain that. And then the last thing, that there are several issues which are sort of ad hoc. So ad hoc issues, these are not really problem, but things that don't look nice. Okay, and you see that the standard model is based on a lot of symmetries. We are identifying new particles based on symmetries and symmetry properties. So there are some things which are ad hoc and you don't like that. So there is this what's called the hierarchy problem. Which is essentially within the framework of the standard model, all the masses are obtained by interaction with what's called the Higgs field. And the Higgs itself, it's a particle which has a mass, and it was measured. The problem is that it requires some fine-tuning of the mass to get the universe that we see. And we don't like that fine-tuning. If you just slightly change the mass of the Higgs, the universe will be completely different than the way it is now. So we don't like that, right? We like a theory which does not require fine-tuning of the parameters. So fine-tuning, fine-tuning of the Higgs mass. I said there are 19 free parameters. Which are not nice. And there is the strong CP. CP is a charge parity. Breaking the CP term. Okay, in addition to continuous symmetries, this is something which we will discuss. In addition to continuous symmetries, there are three symmetries which are reversal. So there is a time reversal, right, between future and past. There is a space reversal, that's called parity, between right and left. And there is also a charge reversal between electrons and anti-electrons. positive and negative charges. And we, in principle, since we know that universe is made of matter, not antimatter, that means that there must be some term that breaks the symmetry, the CNP. This is something which we will discuss. But we've never seen any term like that. So we don't know what happens. Yes?
In modern physics, we assume that neutrinos are traveling the speed of light, so say that's incorrect.
Yes, we know today that they are very close to the speed of light, but they're not exactly.
Have we proved? We did not prove it that they are moving with the speed of light, but we proved that they are not moving with the speed of light.
Of course, this was a detection that was a Nobel Prize.
Okay.
It was detected that they are not. They have masses. If they have masses, then that's called neutrino oscillation. So you can read about that. And I don't know if we'll have time to discuss that in this course.
In which year?
It's quite recent. Neutrino oscillations. Between the early 2000s, I think.
Okay.
Yes, there were other questions. Yeah.
Can you explain about the dark matter and dark energy? I didn't understand, like 100% is energy or matter? Like,
We don't know. It's
no,
energy.
because
It's energy dark. We don't know what is dark energy. We just know that the universe, dark matter is something which we see, is a matter that we see that is affected by gravitational potential, but we don't see it. It does not emit light. That's why it's called dark matter. Dark energy is we see that the universe accelerates, and we don't know why it is being accelerated. So we call it a vacuum energy as well. Now, since energy and mass are the same, right? E is equal to mc squared. They have the same units, and it's the same.
okay, so what we're studying now is about the 5% that we do.
This is the matter. Yeah, this is this matter. This is the sun. This is everything we see and we can test and measure in the lab. Okay? It contains only 5% of the energy content in the universe.
That's depressing a bit.
I should have said no, the opposite. That means that there's plenty of room to have new Nobel Prizes in the future. Right? If you think we know everything, that's depressing. It's much more interesting if we don't know. Yeah.
מה זה ה-CP term?
CP is it's called charge parity violation. Charge parity violation. We'll discuss that later. Okay. So after we said what it is not, then let's say what it is yes. So this is the incompleteness of the standard model. So we have to start by admitting the limitations of what we're going to say in this course. What it is yes. So the standard model is defined by the Lagrangian. So we will put Lagrangians around here. Which the Lagrangian is defined by the symmetry. So we really care about symmetries in the Lagrangian. And you'll see in a few weeks' time exactly what I mean. Some model is defined by the Lagrangian, which is defined, if it's defined is the right word, let's say defined by the symmetries. It feels. So, within the standard model, the outcome of all these symmetries in the Lagrangians would be particles. So, the end result are particles. Now, within the standard model, there are three types of particles. Now, I should say that today all the particles that were predicted by the standard model were detected. So everything is, all were detected. In this sense, the discovery of the Higgs is very boring because there was no sign for additional particles in there. It's good for Higgs, but it's not so good for other people who would like to have other particles in there. Now, the particles which in the standard model are divided into three categories. And so there are three categories of particles. So the first category is the fundamental fermions. I assume everybody here knows what is a fermion. Is there anybody who does not know what is a fermion? Take a course in statistical physics, or
We're taking
okay?
mechanics too.
No. But in thermodynamics, they don't speak about fermions and bosons.
They mention it, but they don't explain the difference and why it is like that.
Different statistics. They obey the Fermi-Dirac statistics. They obey the Bose-Einstein statistics. The Bose-Einstein condensation.
Not
They
in,
don't.
not in thermodynamics,
Fermi-
only in statistical mechanics.
They don't speak about that. Oh yeah. Okay.
פשוט תעבור ללמד את כל הקורסים.
תודה.
ואז התואר יהיה באמת...
תודה. They all have spin half. The spin statistics theorem. All the fermions have half spin, half integer spin. All the bosons have full integer spin. So fundamental fermions all have spin 1/2. מה זה spin אתם יודעים? These are also known as matter particles. Okay, so we have the fundamental particles, which are all fermions. Then we have interactions, right? If we are something interesting to happen, then we need interactions between the particles. So interactions between the fermions. They come because of several symmetries, and they are transmitted by other particles by spin 1 bosons. Right? So interactions are transmitted by spin 1 bosons. So also known as vector bosons or gauge bosons. Some reasons which will become clear down the line. So, which fundamental interactions we have? Which forces we have? Right, so the first one is electromagnetic. And what is the gauge boson? What is the theory? What? Photon, right. The gauge boson, the photon, and the theory is called quantum electrodynamics, QED. This one we'll go through. QED. And the particle is called a photon.
QED is in introduction to quantum field, right?
Quantum electrodynamics.
Okay.
That's QED. Then we have strong is the weak, so we have the weak interaction. What is the weak interaction doing? Radioactivity. All the decays. All the decays that we're seeing is because of the weak interaction. The theory is called electroweak. EW. It's electroweak. What are the particles? Do you know?
Gallons.
What?
Z and W.
Z and W.
The Z and W, right? The Z and W, very good. So we have the Z, W plus minus, and the Z 0 boson. These are the particles. Then we have strong. You know how we call the theory?
Quantum chromodynamics.
Right, that's quantum chromodynamics. There are colors there. Not really colors. UCD, that's quantum chromodynamics. How do we call the particles? Gluons. That's the colors that you might have heard about the quarks, right? Red, green, and blue. Maybe related with marijuana in the 1960s, I don't know. It was not there. Now, what we don't have? Gravity, right? Gravity is not here, so no gravity. But if there will be, then how will you call a particle? Graviton.
They will have spin too, right?
Yeah, but not here. It's not there. So we said there are three categories, three different categories. So one is the fundamental fermions, the second is the interactions, which within the standard model are gauge bosons. And the third category is the Higgs, right? Is the Higgs particle. This is the particle that gives the mass to the other particles by interaction between them. You'll see how interaction between particles can generate mass. Mechanism. That's a spin 0 boson. This is a spin 0 boson. And the mass of the Higgs, if you care, is 125 GeV.
What is the mass?
What?
What is the mass?
It's the mass of the Higgs.
No, what's the number?
125 GeV.
Oh, okay.
Isn't it a lot for particles?
No. There are heavier particles in Higgs. No, there are no heavier. This is the heaviest. The top is quite close. It's nearly 200 GeV. That's right. Yeah. The top is heavier than Higgs, but it's more difficult to detect the Higgs than the top. Reason is, of course, because the top can decay into photons, and the Higgs do not decay into photons. They don't have mass, so you don't see the photons directly, just indirectly. So it's related. What's called a symmetry break in electroweak. So it's spontaneous symmetry breaking. And during that spontaneous symmetry breaking, the other particles gain from mass. I think I'm over time. Yeah, question? Yeah.
How can we talk about mass without talk about gravity? Why is not?
For me, right now, within the framework of the, you're right that the mass has an issue with gravity. Mass is related to gravity. The mass here is a fundamental property of a particle. You'll see that we don't have time now, so on Thursday. We assign to each particle, the way I think of it is to think of a particle as, element in a quantum space. And to that particle, I assign a few quantum numbers, such as charge, or a weak charge, right, or a mass. So for me, a mass is just a number that I assign to each particle. Right? I can measure it, same way I can measure a charge. Now, you'll see that there are certain conservation laws which must be obeyed. For example, a heavy particle cannot decay into, a light particle cannot decay into a heavy particle. But the heavy particle can decay into lighter particles, provided that the masses are conserved. Not the masses, but the environments. Okay?
So we find a different definition for mass with properties that match the.
I don't think it's a different definition, but yeah, it's a good question. What is mass? But then we go to that in the course of general relativity much deeper. Here I just look at the mass as a property of an elementary particle or of each of the each of the gauge bosons. It's just a property which is there. I need that for the calculations because that can tell me which interactions can happen and which interactions cannot happen in nature. And that's it. It's, within the realm of, I mean, that's part of the problem, I guess, that gravity is not part of it. Okay? Right, so see you on Thursday. I should give you the first problem set today. Again, it's not, you'll see, it's not going to be too difficult. The idea is not to be difficult, the idea is that you make sure that you understand here. I even went the special activity slightly above what is actually needed for that course, but you know, it's always good to have a few wasted time. Yes?
The exercise will be about special relativity.
The exercise will be about everything you learned so far.
Mostly special relativity.
What we did, reduction, natural units, special relativity, everything we did so far.